Before kind of Fast.ai was converted to a pip package, it was a lot more easier to kind of jump around code. Now, since it's
Yeah.
been converted to a pip package, how do you jump around the code? You just download it from Git and then open it up in Visual Studio and then jump around over there, or is there an easier way?
Yeah, the easy way is to get it onto Google Colab.
Okay.
So if you can start up, if you can, I think the first thing you have to do is transfer. Say if you download it from Git, you can transfer it into your Google Drive, and then from there you can open it in Colab.
Are you talking of the IPy notebooks, or are you talking
Yes.
of? Okay, yeah.
Yes,
So
the iPy.
I'm saying in IPy notebooks now. Let's say if you were to look at some function, let's say you were trying to look at the fit function.
Yes.
So the traditional way would be like question mark fit. But then you want to dig deeper and deeper. So I'm asking
Yes.
for that part of it. Question mark, you kind of lose track about how to move forward and backwards in that. So right.
I think question mark just brings up the I think it just brings up the code, right?
Yes, right.
It just lets you see what's inside. And you mean now you want to move back and forth?
Right. And then in fit, let's say you have a call to the learner. So now you want to see how the learner works or which learner is being called.
Okay. Okay. To do this, you have to use not question mark. You have to use the debugger. So there's this function inside the Jupyter notebook called debug, and you call it by %debug.
Right. So %debug will be called if my program crashes. So basically, let me kind of give you some background of what I'm trying to look for. So let's say, for example, if I was trying to look at how the unit learner works, you would where do you set the set trace if you were trying to do that?
I see. I haven't explored the debugger, but that's what I understand is that it's just you call the debugger and then you set the trace where you want to see the behavior. So and I guess what it does is it executes down to set trace, and then you can step forward and backward. And I understand your question now. I don't know how to do that. I do plan to explore that myself. I haven't really explored the debugger yet, but that's a really good question.
Okay.
And you might start by by looking it up in Jupyter's docs.
Okay. Yeah, because it's not such a user-friendly GUI. You have to type in commands. Yeah. So I was just wondering if someone has some experience in jumping around code. Yeah.
Does anyone online here can answer the question? Just jump in if you can. Okay, well, I'm going to make a note that was a question, and maybe I'll be able to say something next time.
Cool.
Actually, Prashant, could I ask you to to remind me towards the end of the meeting that I'm to set up the CS224
sure.
meetup? Thanks. Maybe 10 minutes before 10 or something. 10 minutes before 10. Maybe that's a good time, and I'll just set it up, and then people who are showing up can have some place to come.
Will do that.
Thank you. Thank you. Oh, okay. I didn't notice it was already time to start. Okay, so we pretty much finished with the Notebook 03 mini batch training. Although there were a few things I wanted to cover, but well, maybe I'll just try to jump in and do that before I do this. So let me share. Let me stop sharing this and start sharing the notebook. Let's see. That. There. Okay, you should be seeing the 04 callbacks now. But I'm going. Is that what's set in everybody's screen now?
Yep.
Okay, I'm going to switch to 03 mini batch. There's a couple of things that I wanted to look at. You know, Jeremy says with some rancor that he's upset that, you know, the mathematicians keep normal people out of this stuff by using Greek letters, which is good, and it's good to learn the Greek letters, like Jeremy said. But there's another thing that keeps people out, and that's extremely complex code that's written in really small, that's written in a very compact way by extremely good software engineers. And when somebody looks at that for the first time, what the hell they're looking at, and that can really kill somebody's motivation, because they say, I don't understand at all what the hell's going on there. How am I ever going to understand this stuff? So there's a couple of places in this code where I think I see things like that, and I want to find them. For example, whenever I'm going to do a search, whenever they use -1, that will throw you. I'm sure that's thrown you before. Whenever they use slices, whenever they use -1 in the context of a slice, and it's really hard to find the documentation for that. You know, it's really hard to look up what does -1 mean in Python. I don't even know how to frame the question to get Google to give me the answer. So let's look at this. For example, this very compact way of writing softmax.
Sorry, Joseph. I still see your fourth notebook. I don't know if that's only me or others too.
I'm sorry, what's the question?
I'd still see your 04 callbacks.
Oh, okay, thank you for telling me. I'm going to stop sharing that and share what I want to share, which is the third notebook. Okay, now we should be inside the third notebook. Is that what you're seeing?
Yeah.
Great. Okay, so just as an example, let's look at the Softmax function, the way it's implemented here. There's a lot of things going on, and let's just try to break it down. The first thing you can see, let me just refactor just a bit. We're computing this thing. Okay, so we've got this thing called X, the input, and the input is remember, it's going to be the actual pixel files broken down into flattened. So X, a typical X, one X is going to be 784. Sorry, it's going to be one row and 784 columns corresponding to the pixels in the 28 by 28 matrix, right? So what are we going to do with that? We're going to implement this formula, the Softmax formula over here, where the Softmax, the ith component of the Softmax is e to the xi, that is the ith value of x, divided by the sum of all of the e to the x's, right? So, the input, let's see.
So X is just 10 dimensional, right? Here, Joseph?
Sorry?
X is just 10 dimensions.
X, let's see. That's right. I'm sorry. Yes, a good catch. X is the output, not the input. It's the output of the activation at the last linear layer. So you have 10 dimensions, right? So x dot x is going to be so x dot x is going to be one of the activations is going to be the exponentiation of one of the activations, and then x dot x on the denominator, x dot sum of -1 keep dim true. This is what's hard to follow. This, first of all, this chaining thing where you can do an operation and then dot and then do another operation on it. And this is like an aggregating operation. So the first thing to do is let's look at the denominator. I think that's as it stands by itself, part of the denominator. So x.x.sum, what does that mean? It means take the 10-dimensional output and exponentiate each one, and then sum them along the last dimension. That's what this -1 means. It means sum along the last dimension. So if there was 2 dimensions, then it would sum along the second dimension. It's just a way so you don't have to keep track of which dimension you're trying to sum over. You just keep in mind that, oh, it's just the last one that I'm going to sum over. So, okay, then what happens? And keep dim equals true means that normally when you sum over one of the dimensions, you get to collapse that, right? So if you have a 10-dimensional vector and you sum over that, you end up with a 1-dimensional vector, right? So what this part is doing, keep dim equals true, says don't squeeze, don't collapse the last dimension, leave it there as a 1. Okay, does that make sense? And then, okay, so then the next thing you do after you complete that is you take the log of it. That's what this dot log is. Okay, and then the numerator, let's see, x dot x. You know what? I got lost here. I think I have to. You have to include all of that. If I want just the denominator, I should have included only up to the last parentheses here. This is what I want, right? Because the last parentheses belongs to the expression. The last parentheses here is paired with the first parentheses here. So I'm looking at part of the denominator, which is the sum over all of the exponentials, but then keeping the dimension equal true. So I'm trying to remember if this x dot x is 10 by 1, and when you sum it, you could end up with, since you've summed over the 10 dimensions and you only have, it's really one number, you could have a scalar as an output, but it says no, keep the dimension equals true. In other words, keep that last dimension. And then the last thing here is, okay, so then come back. Now this thing means put the numerator there too. So x dot x is a vector of all the exponentials. Okay, so what you have here is all of these things normalized by the sum, all of the exponentiated weights normalized by the sum, and then finally you take the log, and that makes it the log sum x, right? So that's what that is. So I wanted to just cover that. Something there's some places in the notation where it looks really thorny, and it helps to actually look at it and pry it apart and understand what's really going on. Can anybody think of any other examples where the software engineering is so slick that it's kind of throwing you off? All right, well then, let's see. Okay, I'll leave it at that then. So now I figure I finished notebook 3, which is one of the things I wanted to do. So the first thing I wanted to do, now let me go back to sharing the PowerPoint just for a moment. There it is. Okay. Are we seeing the PowerPoint now?
Not yet.
Oh, okay. I thought I just shared it. Right. Back here. Share the PowerPoint and share. How about now? See the PowerPoint?
Yep.
All right,
there.
great, thank you. All right. Now there is a way to view this in the presentation mode. I'm going to try to do that. Let's see. Well, I had it before. I lost that. So that's okay. Slide. I'll just leave it. All right. Going move down.
I'm sorry.
Yes.
So the screen is sort of compressed into a line in the middle of the screen. So I think we may have lost what you're trying to show.
Yeah, let me stop and resume. And how about now?
Yep, we can see it.
Great, thank you. Okay, so what I want to do here is finish review of Notebook 3, and that was just that one thing about notation that I just talked about. And then I want to go, the main part of this lesson is just going to be a total review of Notebook 4. And then I'm going to, if I have time at the end, I'll review Notebook 5. And then we'll be truly done with Chapter 9. It really took us 3 intense lessons to get through. And, you know, it's really, let's see, it's really about 2.5 hours, and it's really 3 45-minute sessions. So, yeah, it took me 3 sessions to get, it will have taken us 3 sessions to get through it, if I can get through this today. All right, next. Page down. Page down is not working. All right. Just have to do it manually. Oh, actually, a few other things summarizing the third notebook. So here are the PyTorch classes that we're using. There's the Torch NN neural network, the Torch NN.module, and then all these other classes that we essentially built the things that they do for us. So now we get to use the official PyTorch versions of them. So we built the optimizer, the data set, the data loader, with the shuffle argument and the batch size input and so on. So now we get to use these official PyTorch classes because of what we did last time. And then there was this one PyTorch NN.functional that we also built the functionality that we wanted, that we needed from it. And so again, now we get to use it. And PyTorch NN.functional module has a bunch of activation functions, a selection of the activation functions that people most commonly use, and loss functions that people commonly use as well. In our case, we were using just the ReLU activation function and the cross-entropy loss function. And then it also has pre-built layers such as convolutional and linear layers. And we've used it for that as well. And we're allowed to use it for that as well because we built our own linear layers, and next time we'll build our own convolutional layer. So the way we use it is, you've seen it in Notebook 3, import as F, and then this is what Jeremy says people usually do, and then you can just call the functions by F dot and then the name of the function. So if you want a ReLU, you can call F dot ReLU. If you want the NLL loss, you just call that. If you want the log softmax, you call that. Negative log, NLL stands for negative log likelihood. We can get F dot cross entropy for the cross entropy loss function. And we built that, and then he mentions that it's the same as the negative log likelihood loss as a function of the softmax. And we built this, if you remember, that's in Notebook 3. And then we can actually call out the loss function equals F dot cross entropy. And I think I believe I need these parentheses like that. Yeah. Okay, so now I'm finished with Notebook 3. Let's go to Notebook 4. So this is the concept of callbacks. I'm going back to this blog post from Pierre Owanes, which has some nice graphics in it. And he started out by giving this graphic of what the training loop looks like. And you have a model, you run the model, you compute the loss function, you do the back propagation, that's the gradient step. Then you do the updates, you update the parameters using the gradients, and then you cycle through that. That's the training loop. Now, the concept of callbacks is we insert little markers in the middle in various intermediate stages, which allow us to do stuff more flexibly. So in between, after we run the model and before we compute the loss function, we insert this callback, which is a function that can do things for us, like keep track of things or print something, or there's a lot more complicated things too. So that's callbacks, and we're going to learn about those this time. I remember when I went through this class the first time, and I didn't go with the notebooks. I was just listening to the lectures, and I got hopelessly lost here because I just couldn't follow it. And it turns out that if you really want to follow it, you really have to work through the notebooks and see what's going on. So I hope that everybody by now has the capability to run the notebooks. And if you don't, I said that you could message me on Slack and I can lead you through it and make sure that you've got that capability. That's really important. If you really want to go through this class and get the most out of it, you need to be able to run the notebooks, and you need to be able to spend some time doing that. Right? Let's see, next slide. So here is an example. This is the training loop after you insert the callbacks in it. And you can see that there's all this very confusing stuff that we didn't see before, a callback handler, this thing called callbacks, all of these weird states on train begin. We can recognize the lines that are outlined by brown. Those are the lines that we recognize from our training loop, but the rest of it has been refactored so much so as to be hardly recognizable. So what we want to do today is go through and see how this got built. All right. Slides. So, and then there's a slide. This is from Jeremy's talk. He says that once you learn how to build callbacks, you can build new ones. And I guess Fast.ai built a lot of little callbacks that are useful, that can be mixed and matched in the program when you write programs. And then, of course, now we know how to write. Once we know how to write callbacks, we can write our own, and that's this last one. So some of these interesting, I haven't played with any of these yet. I'm learning the same stage you are right now. But there's some interesting ones. Mixed precision is something I'd like to try because I have a laptop that can handle mixed precision, and it's supposed to be much faster, where you don't do all the math at the high precision. You do some of the math at lower precision, where it doesn't matter, where the precision doesn't matter. Okay, so now I'm going to stop sharing this because that's as far as I've got in the PowerPoint presentation, and I'm just going to go into the notebook and start reading it through it. So got to have to share this again. Share and then switch. Can everybody see the fourth notebook now?
Yes, I can.
Great. Okay. So what I've done with this, and I just pushed it onto GitHub this morning, is I refactored it to make me happy because I didn't like the way it was written, and it just didn't have a flow that you could follow what was going on. So I refactored it in pretty much minor ways. I mean, mainly I didn't really do anything major. I just sort of added more documentation, and I changed the order of some things, and I made some things look nicer because I don't like using cryptic little things like NH to mean something that I can write out by saying nhidden. And it doesn't take that much more effort to write out nhidden, but then you know what it means. So that's what I've done, some of the things that I've done in here. So, and I also kind of gave headers that show what we're doing. So here it is. I'm just going to run through it, just going to scroll through it, and I'm not really going to say anything. But this is what we're doing. We're taking apart all of these building blocks and showing how we then put them back together into a refactored training loop that has the callbacks in it. And let's see. And then somewhere towards the end of this notebook, Jeremy built this runner class, which is not implemented in Fast.ai version 1, but is definitely going to be implemented in Fast.ai version 2. And I don't know when they plan to release that, but when it comes out, then we'll know how to, we will already know how to use this runner class. Basically, it's Jeremy's version of making the callbacks even easier than they were before and more straightforward. Okay, then there's at the last point, he writes a callback to compute the statistics on the loss function and the metric and so on, and then that's it. So let's just go through this. It's going to be a little bit painstaking, and hopefully we can get through it all in the next 45 minutes or so. So first thing first, you just set up the environment. This is always done at the beginning. We import the code. By importing this notebook 03, that means we're importing everything that's been built up until now. We have access to all the functions and classes that have been built up until now. So you'll notice that at every notebook, you'll always do this. The way this course is structured, you always import all the stuff from previous notebooks first, so that you have access to all the functions and classes that you've defined in the previous lesson. All right, the next thing is this usual thing: get the data set. Just look at the shape to see that it makes sense. And okay, the first thing we're going to do is before we even do the callbacks, we're going to improve the fit function. And Jeremy does this by building an object called the learner object. And the learner object is a container that will basically contain these pieces: the model, the loss function, the optimizer, and the data set. Those four things. And so this is his idea, is to modify. So a lot of this stuff, it's really random when you look at it, when you just sort of try to follow it all in a linear manner. But it helps to look at it like Jeremy and Sylvan did when they built it. They said, what if we could, so it started with something like this, like you see all this stuff going into the fit function. There's all these inputs. What if we could simplify it by building an object, a container for most of those inputs? And then things will be really nice, because if you built that class, then any changes that you made to that container would then, to the things inside it, would then be updated and reflected whenever you want it. And you wouldn't have to keep rewriting these things over and over again. You just call the learner class, and that's what he's doing. So he's building this learner class, which is basically a container for all of these things, right? So he said, what if you could modify the call to fit to look like this? Fit, instead of fit of all this crap, fit of, and you just give it n epochs, and you give it this learner object. So it says, yeah, let's do that. So then he goes on to build this learner class, which is just going to be, as I said, a container for model, loss function, optimizer, and the train data loader and the validation data loader, which together can be the data set. So, and so learner is just going to be this thing, this container that's going to be passed into fit. And he says this will allow us to tweak what's happening inside the training loop in other places of the code. Because the learner class object will be mutable, that means that you can make changes and they will be then reflected whenever you call that object. Changing any of its attributes elsewhere will modify our training loop. All right, so the first thing he does to facilitate building this learner class is he builds this data bunch class. And all the data bunch class is a container to hold the two data loaders. So the data bunch, you get, the inputs are the train data loader and the valid data loader. And remember what a data loader is. It is an object that can generate a random batch. That's all it is. It generates a random batch whenever you call it. So you either want a random batch from the training data set, or you want a non-random batch from the validation set, where you don't have to randomize. All right? So it takes the training data loader, the validation data loader, and the batch size as the inputs, and then it adds the train data set as an attribute. Remember, you can get the train data set out from the train data loader this way. You take the train data loader dot data set. Data loader was defined, if you look back in 03 notebook, so that it has attributes or properties of which are called dot data, which you can get at by calling dot data set. And so you add these attributes of train data loader dot data set and validation data loader dot data set. Now you've got this object called a data bunch. So now we can define the learner class as a container that holds the model, the optimizer, the loss function, and the data bunch. Here, data is just going to be a data bunch. So get model instantiates the model and the optimizer. I think we've seen a function like this in the 03 notebook. So it takes as the input the learning rate and the number of hidden layers, and then it figures out from the data that you gave it. Okay, so the data.trainDS, that's the train data set. Now you can, and the train data set has X and Y as properties. If you go back in notebook 3, you'll see that you can get X and Y out of it. And so X, remember, X is the images, and Y is the label. So if you take the shape of the image input, it's going to be 10,000 by 784, right? And so the shape is 10,000 by 784. The 0th element of the shape is 10,000. The 1th element of the shape is the 784, and that's number of columns. Here I refactored a little bit. Again, I don't like these cryptic things where originally this was defined as m equals that, and who knows what m means. I want my variable names to always be descriptive so that I can look at it and understand what it's telling me. So that's why I changed LR. I don't like LR because I want to say I might not know what LR means, but if I write learning rate, then I always know what that means. And NH, I don't like NH, but I like N hidden because that tells me the number of hidden layers. It doesn't take that much more energy or effort to write it out, so I do that. N columns instead of M. N columns tells me the number of columns in my input, and then the rest of it is just as Jeremy wrote it, except I've replaced all of the variable names with the ones that I created. Okay, and also BS for batch size. I write out batch size. Why not? It doesn't take that much more work, and you never get confused about what the variable means. So, so here we are, and so this get model, it returns the model. First, it builds the model, then it returns the model. It returns the optimizer with the given learning rate. Okay, and okay, now that we've built this get model, we can run the get when we need it. We can run the get model to give us the model and the optimizer. Those are two of the inputs that we're going to need for our learner class. And so now let's build the learner class. All it is going to be a container for these four things: the model, the optimizer, the loss function, and the data. So you call learner with those things as the inputs, and then it just the only thing it does is it initializes these attributes of itself with the things that you gave it as inputs right here. So is everybody up with me now? As I said last time, I want you to break in and ask questions if you have them. Don't be shy. If everybody breaks in all at once and asks too many questions and I can't get through the lecture, then I'll have to say something. But I don't think that's going to happen. So so go ahead and ask questions anytime you have it. Just break in and ask a question. All right. So now we have defined this learner class, and now we can refactor the fit function according to the plan that we started with right here. Remember, that was, what if we could have this new cool way to call the fit function where we call it with a learner and all we need is the number of epochs in the learner. By the way, I like when Jeremy calls this new fit function, he calls it as fit of one learner. And then who knows what the one means? I mean, sometimes he calls it as fit of three learner, and you're supposed to interpret that to mean, oh, there's 3 epochs. But I don't like that, so I refactored and put the n epochs at the end where it's a keyword argument, and so you can make it whatever you want, but you can specify it. So here's my fit function. It's just, instead of the n epochs being up front, the learn object is up front, and the n epochs is following that. Okay, so n epochs is a keyword argument, and it's just an integer. And so first you loop through for epochs in range of n epochs, that is, loop through all the epochs. And then for each epoch, you do a training phase and a prediction phase. And then after you're done with that, then you compute the loss and the average accuracy, and you print them out. And that's what this new refactored function is going to do. So let's look inside a little bit. What's the training phase do? Now we're going to loop over the batches for XB, YB in learn.data.train.dl. Remember, train.dl is generating batches. And when you loop through, it's an iterable, so when you loop through it, it's going to generate all the batches. It's going to go through the entire data set and generate the batches one at a time. And each time you get a batch, you calculate the loss function. You first have to create the model. That's what's being done inside here. And then once you have the and remember, when you run learn.model, it gives you the predictions. So this thing is the predictions, and this thing are the real labels, and then the loss function is calculated, as you saw last time, by comparing the real labels with the predicted labels. And in our case, the loss function we've given it is the cross entropy loss function. So, okay, so it's the standard thing. You do the predictions, you compute the loss function, you then do the back propagation. That's this step. Then you compute the steps for the parameter updates, and you make the parameter updates. That's what this step does. And then finally, you zero out the gradients to prepare for the next batch. Right? So that's what the training phase of the loop does. And that prediction phase, now we're going to call the model.eval, which means we're only going to predict on the validation set. So since we're only predicting, we don't need gradients, and we're not going to do any back propagation. So that's why we do this with torch no grad. Remember, that turns off the requires grad switch. It makes requires grad equal false. Each tensor has a requires grad switch, remember. Okay, we initialize the total loss and the total accuracy to 0, and then we loop through, again, the validation data loader to get the batches for the validation set. We make the prediction. Remember, I said before, when you call the model, learn.model of XB, that gives you the predictions. We called it up here to do the same thing. In fact, it might be nice just for people who aren't software engineers if we refactor this just a little bit and say pred, again, pred equals learn.model of XB, like that, and then see that makes it nicer to look at, even though it's not as compact. I know Jeremy is really all in about writing compact code. As a software engineer, you take pride in that, but that puts people off at the very beginning, so if they can't follow it. So I think it's much nicer to take some time, expand the code out, don't try to write everything in one line, just so people can follow it a little bit easier. So that's why you'll notice wherever Jeremy's fond of writing these functions all on one line, the definition, blah, blah, and then a return, blah, blah, all on one line. Again, for me, that's too compact to look at. I like to expand it out just at the beginning so people can see more clearly what's going on. So we've done this. We've done the predictions. Now we calculate the loss function. The learn object has the loss function, remember, and by comparing the predicted labels with the actual labels, we can compute the loss function. We can compute that. We can accumulate the change in the loss function. And the same thing with the accuracy. We compute the accuracy by comparing the predictions with the actual labels, and then we accumulate the next term in the accuracy that's corresponding to that batch. And then once we're all done, we get the number of let's see, we are now in, we get the number of total data points in the validation data set. That's n valid. Again, I named it in Jeremy's code or Sylvan's code, it's n equals. I don't like using n equals. One thing is it's hard to search for it. If you decide that you want to refactor and you want to replace your n's with something else, it's really hard if you try to search for n, you're going to get hits everywhere because lots of words have n's in them. So it's not a good practice to name variables n. So anyway, so I called it nValid instead of n to be descriptive. It tells me the number of elements in my validation set. And then it's just the length of the data loader. And all I need that for is I want to take the average of the loss function, the average of the accuracy, by dividing my total loss that I've accumulated after I loop through all the batches by the total number of objects in the total number of examples in the validation set right here. So that's all I did. I just got the number of objects. I could even label this average loss and accuracy. So yeah, that's what I've done here. And then you print it. You print the epoch number. Remember, this is in the middle of looping through epochs. So you print the epoch number, you print the average loss and the average accuracy. And so, you know, if n epochs is 3, then epoch is going to loop through 0, 1, and 2, right? And so as you finish, you print out the epoch number, the average loss, and the average accuracy. And nValid is not the total number of examples in your validation data set. It's the total number of examples in the batch, in this particular batch. And so this takes care of the case where, you know, remember the last batch is often uneven. It may not have, since the number of batches may not evenly divide the size of the sample, the last batch is going to might have a different number of samples in it. And this takes care of that because I compute the number of examples in every batch. Or did I do that? Let's see. Maybe that doesn't make sense. What I just said.
I don't think
nValid is the total number of examples in the validation set. Sorry, someone had a comment?
Yeah, sorry, just wanted to reiterate that it's the total number of.
Yes, you're correct. Is this John?
No, this is Prashant.
Oh, Prashant. Okay, yes, you're right. Okay, so we'll move on. Okay, so the next thing we're going to do, prepare for mini batch training. The first thing we're going to do, so what we've done is we've refactored our fit function according to the plan that we had above. The next thing we got to do is, if we want to run a loop, is we want to prepare for the mini batch training by packaging up our data in a data bunch. And that's what I should do here. I should say that. That's what we're doing.
Joseph, before we move on to the next part, just wanted to clarify the model.eval. Learn.model.eval, that's basically telling you not to perform any dropout or batch norm. That's what that is doing there.
That's right. Although we haven't implemented it that way yet.
Right. Right.
What it's doing for us now is it's saying basically you don't have to do any backpropagation. You're just going to in the evaluation phase, all you're doing is getting the prediction. But yeah, when we do this, when we make the full-blown loop, then it means, you know, don't do the dropouts, don't do any of the regularization things. You're just going to do the predictions. That's right.
So let me ask a quick question. Average
yes.
loss and average accuracy, they're not concerned with training. Just validation.
Let's see. Let me see. No, they are actually. Oh, well, okay. That is validation, right? Maybe I.
No,
yeah, you're right. They're only. That's right. You're right. You're just looking at the validation. The idea is that you want to run the model on the validation set and then see what the loss function says, because you always want to make sure that it's reasonable compared to the training loss. In other words, did your validation loss get much bigger than the training loss or not? That's what you want to see here. And also, the metric has nothing to do with training. You're only evaluating it on the validation set. So yes, you're right. The accuracy is our metric, and we only care about the validation set. Okay, so to prepare for mini batch training, all we have to do is package up the data into a data bunch. That's what we're doing here. And So here it is. We specify the batch size. We create this data bunch object, which is called data. So data bunch is a class, and here we're instantiating the class and make an actual object here. Get DLs. I believe this get DLs function was created in the 03 notebook, and what it's doing is it's basically going. This star here forces you to go through. Remember, these data loaders, these DSs are iterables, and the star is forcing you to go through. Oh, and the get DLs, when you operate on get DL, the get DL function gives you as an output the data loaders, and the data loaders are themselves iterables, so they're generators. And so this star forces you to actually run through every possible value of the, in other words, iterate through all the possible values of the generators of these data loaders. That's what this star is doing. I wrote the note here. The star forces you to generate and process the entire sample. Okay. And then the batch size is the input. You want to, if you're going to create a data bunch and you're going to create these batches, you got to tell it what the batch size is. So you specify that here.
Just a quick question.
Yes, sir.
From my understanding, I thought star was because it kind of returns two data loaders. You have valid and trained, so you get back like two parts, like a tuple. So I thought that kind of opened it up.
That's true too. I mean, I think that. Let's see. You're right there, and that's part of it.
Operator, if I'm not wrong. I think we can Google that and check that later.
So you're right. Get DLs returns a tuple, and the tuple is train DL, valid DL. It's those two things. And the star forces you to get both of those. But it also forces you to go through and generate the entire sample. In other words, generate the batches until you've processed the entire sample. So
cool.
and you can see that when you look at the output. So this is a data object, data.trainDL. It has a part of it. One of its properties is the train data loader. And remember, the train data loader has a property of dataset that we gave it. And then the dataset has properties of X and Y, X being the images and Y being the labels. So you can see that once we've done this, we get the whole thing, all of them, right? We forced it, this star forces you to process the entire dataset. And that's why Jeremy shows this example here, where you can actually see that it's all there. Okay, so now that we've done this piece, now we can actually instantiate a learner object. We have all the pieces that go into it. We have the loss function. We've already defined the data that we just defined, and then get model. Remember, that gives us the model, and it gives us the optimizer. And again, in that case, that's what this star is doing. It's the output of get model is a tuple, which has in it model and optimizer, and the star is forcing us to add both of them, to add both elements of the tuple as the input. So there's our learner object. Now that we have the learner object, we know how to instantiate a mini batch training loop. Remember, the fit function we've designed so that it returns the loss functions and the accuracy. So loss and accuracy are the outputs. Learn and epochs is the input. And this is what I use this what do we call this thing again? It's you can't put n epochs before learn, because otherwise it won't let you do this. It won't let you specify it. There's a name for it, and I'm trying to remember what that name is. I wrote it down up here. Where did I write it? A keyword, that's right. It's a keyword argument right here. N epochs is a keyword argument, which means that you can specify it upon input. And but the rules of Python are such that the keyword arguments have to come at the end of the inputs, at the input list, and that's why I had to move this. Jeremy and Sylvan had it as the first input. And it may be that that this was a bad idea. We'll see later. Maybe they planned everything else so that you need to have n epochs up front. we'll see how that plays out in the next few notebooks. But right now, I just think it's a better idea to put to have n epochs as a keyword argument and put it at the end. So I haven't been executing. Let's execute everything and actually see this work. Okay. We've made the learn object. We can now instantiate the mini batch training loop and watch it train. And there's epoch 0 because we only wanted one epoch. The loss function is 0.1859, which is reasonably low, and the accuracy is 94%, which is good, so we're good. All right, now comes the main part of this notebook, which is adding the callbacks. So what are callbacks? Callbacks are functions, first of all, and they can be set to initiate desired sequences of actions at various stages in the training process. So this is, and Jeremy says they will allow us to simplify the training loop and to provide added flexibility. So the first thing that he does before we run the callbacks is he takes apart the inside of the training loop in an interesting way. In other words, you have a special function that just processes one batch. So you can see what it's doing. It's running the model, getting the predictions. It's calculating the loss function given the predictions and the labels. It's doing the back propagation. It's doing the step, meaning it's doing the parameter updates. That's what opt.step does. And then it zeroes out the gradients. It does all the things that we are familiar with that you do when you process a batch. So now you can refactor this fit function in another way. You can loop over the epochs, and for each epoch, you can loop over the batches. And that's what's going on here. One batch, star B, again, forces it to go through the next batch. Star B makes it go through the next batch. So, and again, I would, yeah. So this is sort of the pseudocode for what he's going to do now. And now we're going to start by defining a callback class. And they've identified a series of 9 callbacks associated with various stages in the training process that they found through their own trial and error and through their own experience to be useful. And the way that they've set this up is that each callback is going to return true. You can see it. Every one of them returns true. And some of them are really simple. It just begin fit just takes as an input the learner object, and then that's all it does, and then it returns true. After fit doesn't do anything. It just returns true. Begin epoch takes as input the epoch, and then returns true. So the epoch is the current number, you know, like 0 or 1 or 2. Begin validate just returns true. These are just marking certain points in the training cycle. After epoch, again, just returns true. It doesn't do anything else. Begin batch takes as input the pieces of the batch, the images and the labels, and that's all it does. Then it returns true. After loss, just calculates the loss function. It takes as input the loss function. Sorry, and then it returns true. After backward, which means after back propagation, just returns true. After step, just returns true. So these are just 9 little functions that they package together in this class called Callback. Next, they build a class called the Callback Handler class, and this class collects together a set of methods that when you give it a list of callbacks, it sets a flag for each callback included in the list, and then finally it adds another method called doStop that returns the learn.stop flag if it exists. Otherwise, it sets the learn.stop flag to false. So learn.stop might not have a flag because it doesn't have a flag the way we defined it. So if it doesn't exist, then it just sets that, it adds that property to the learner, and that is the learn.stop flag, and sets it to false. So let's go through this. Here are the 9, well, it has an initializer that takes the list of callbacks. It's expecting a list of callbacks. If it doesn't get a list, then it sets this thing to an empty list. Does that make sense? So if there is a callback list as an input, then self.callbacks becomes that callbacks list. Otherwise, self.callbacks becomes an empty list. So that's its initializer method. And then the rest of it is these 9 methods corresponding to the 9 things that we saw in the callback class. And then an extra method at the end called doStop, which, let's see, it's this try catch loop, or actually try finally loop. It tries to return self.learn.stop, but if the learner doesn't have a stop flag defined, then it will default to this finally thing, and it will set that flag to false. That's what I was saying before. So this stop flag is going to be used later on to decide when you stop. So let's just go through. The begin fit class takes the learner and let's see, what is it? Self.intrain, self.learn, self.intrain. Intrain is a flag that says whether you're in the training part of the loop or the evaluation part of the loop. They don't have a special flag for evaluation. So it's intrain equals true means you're in the training phase. Intrain equals false means you're in the evaluation phase. And so begin fit sets the training loop to be true. Tells you're in the. It sets the stop to be false. It sets in Jeremy and Sylvain's code. This is called res. Res meaning, I guess it's shorthand for results, but I renamed it to be called state. And state just tells you what, this particular callback, what its state is, whether it's true or false. It's just a Boolean. So for callback and self.callbacks, the state equals state, and it's a Boolean thing here. State equals state and callback.begin fit learn. So what it's doing is it's anding these two things together. Now, state is already set to be true, so that part is going to be true. So the output of state is just going to be whatever callback.begin fit learn is. So it basically says that if you're in the begin fit stage of your callback, then you should return true. And the other ones are set similarly. After fit, the state is, let's see, the state is not self.intrain. So if you're in training, then after fit should be, this is going to be true. In train is going to be true if you're in the training phase. Then not this thing is going to be false. So the state for after fit is false, meaning that you don't want to set that yet. So that's what it's doing. It's going to return, if you're in training, it's going to return false. It's not after the fit yet. Begin epoch tells you whether you're at the beginning of a new epoch. So it says let's see, self.learn.model.train. So epoch. I'm not sure why learn isn't listed as an input here, but anyway, you can get away with that in Python. So self.learn.model.train. Oh, begin. Okay, so so what this does, it actually causes this. This is the first callback that actually makes something happen. It actually initiates the training, and then it says it sets this training flag to be true. And then let's see, for callback and self.callbacks, this is again this funny statement. It's a funny Boolean combination. State gets replaced with state and callback.begin epoch of epoch. So state, remember here, is true. And for this thing to end up being true, this thing also has to be true. Callback.begin epoch of epoch has to be true. So begin epoch has to be, you have to be at the beginning of an epoch, in other words, and then it's going to return true.
Joseph, I have a question here.
Yes, sir.
Yeah, so when we call self.learn.model.train, that brackets, So are we putting any inputs in those train function, like, or are we just calling like this?
Well, the model, that's a really good question. So the learner already has all the inputs. Remember the learn object? We built that, and it has everything we need in it, right? So that's and model is one of its methods, and train is one of the methods of model. So everything's there. We didn't have to give it any inputs. I'm just a little, yeah, I'm just a little bit. I was expecting to see learn as an input here.
Just to clarify one thing over there, Joseph.
Yes, sir.
At self.model.train and self.learn.model.train and self.learn.model.eval, they're basically two flags that basically tell whether you're in the training phase or you're in the eval phase. So
they're actually more than flags. They're actually these are actually functions. So this statement actually forces you to start training. It actually executes the training.
Isn't it just a flag which basically tells the model that you're in training phase, so include all the regularization stuff, whereas model.eval
that was the in-train. Remember this self.in-train this is the flag that tells you whether you're in training or in evaluation.
So actually, if you do scroll up back to the previous learner, before we did the fix, further up.
Yeah, I think we were
learner, is this
right here. So here, if you see,
it right here?
Yeah, this exact one where you're
just after training phase.
Yes.
So you're setting that to, so learn.model.train, actually, if you print that out, will give you back the true, which basically is telling you you're in the training phase. And then when you get down to your prediction phase, in prediction phase, you basically don't want to do dropout and batch norm and other regularization stuff.
Yeah, that's right. That's right. But okay, I see what you're saying. You're saying that this is just a flag.
Yeah, which basically tells your model do everything in the training phase here, and the second one tells it do everything in the validation.
Understood. But we have another flag that we've been using here called in-train that does that. Okay, there's this flag here called in-train, and it's set to true when we're training. So this is a flag. You can actually see this is a flag. Let's do something. I think this is more than a flag. So let me see if we can learn.model. Okay, so we built a learner. We have a learner somewhere. Here we go. We've already built it. So let's see something. dir. I want to see what's inside learn. So I can do this dir of learn and see all the things that you can get at. So it has data, it has loss function, it has model. So let me do something. The next step is dir learn.model. See what's in there. And it has things that you can get at, a lot of things that you can get at, but one of them is train. So let's see what that is. So train, and train doesn't have anything that you can get at. But we should look up, because this is this model. Let's go back up and see where we built this model. We have this function called, wait, let me get rid of this so I don't leave it in later.
Sorry, before you get rid of it, can you just remove dir and put learn.model.train open close?
Oh, like this?
Yeah, and just drop the dir.
Thank you. Look, there are things that you can get at. So you have, but anyway, you want me to drop the dir?
Yeah.
Yeah, that's.
This kind of gave us true.
Let's see what that is. So this gives us a. Okay, so this is, so you can see what it does. It's giving us a module list. That's what it's doing. It's not starting the training, like I said. I was wrong when I said it's starting the training list, but it is generating a module list for that's to be used in the training. Does that make sense?
What if we try like eval also, like instead of train, if we add eval to that?
Sorry?
Just replace the train with eval, I mean, the function.
Eval, yes. That's good. Good idea. All right, let's see what happens now. All right, let me just do that in another cell.
True.
So we can compare them. Train, and then insert cell below, and then learn.model.eval, and that's a good suggestion. Let's see what happens. So it's basically the same thing, because the model doesn't change when you do the training or the evaluation. So you recognize this object as a module list, right? It's got the first linear module, the ReLU layer. It's basically all the layers that we want in our fully connected neural network. Linear 1, ReLU, and linear 2. Does that make sense? And why do I have output feature 64? I'm not sure why. I thought output feature should be 10. I'm going to have to look and find out what went wrong. This is really good to look at these things and see what's going on. So can anybody explain why out features is 64? I know that's the batch size, but what I thought is that there was going to be 10 features in the output.
Yeah, that's weird. That should be 10.
That's weird. Okay, I'm going to look into that, and I'll have an answer for you next time. But meanwhile, let's move on. So we got through this callback handler class, and this is a question that we were just handling. We were just taking under consideration. Is what's going on in this place where was it? Sorry, let me look for this again. Model.train. That's it. So learn.model.train builds the module list. So, but what does it do with it?
I remember Jeremy in one of his lectures, he actually puts in a print there, and you can actually see it go true, false, true, false, true, false. I don't know if I'm using that with something else.
Yeah, I don't know. I'm just wondering. I mean, so you're looking at what's in there, but I mean, if you're inside of this fit function, you don't really care. Well, unless you want to print it out. There's no point in doing this.
Yeah, even I remember like something like that. What is mentioned that it's in train or it's in eval phase.
Yes. Yeah. So you could print it. But I think this thing would work if you just commented this out, because all it's doing is, I think, it's just showing you what's in that. It's already there. It's just showing you what's there.
And that is true. It should still. I just found something on Stack Overflow that I posted, and that's what I was saying. Like, it will still work, but in the eval phase, you don't want to remove that because you don't want to be performing batch norm or any regularization when you're finally running your model, right? Because that's going to drop your accuracy. So that's the main reason why you have the model.eval set there, which basically tells internally that don't perform any of the regularization steps.
Right, but doesn't that get taken care of by this in-train thing that we set? We set a flag called in-train somewhere.
From my understanding, the in-train is something that we are doing on our end when you basically
I see.
define a callback.
You're saying this needs to tell PyTorch. This needs to tell PyTorch that we're not. I see. Okay, and so let me just make a note of that. You're saying that this tells PyTorch that we are in eval phase, so no dropout, batch norm, etc.
But Joseph, when you printed them out, like the eval and the train, both were giving the same results. So
yeah, they were. So I'm a little puzzled about that. I'm going to look, like I said, I'm going to look into this in between, and I'll have something for you next time. anyway, so let's go on. We built our data bunch. I think we ran this already. Okay, we instantiated our learn. This was where we were. Instantiate the learner object. Train the model. Oh, we did. Oh, this was just showing us what was in there. Yeah, it's just showing us these things. And now I'm gonna write a question here for myself. Why is each 64 not 10? Sure, there's some kind of an explanation. Anyway, so we get the training. We start the training loop. I think we already did this. Oh, and so we were back. We were way down here, I guess. We were going through the callback handler class. And there are these 9 pieces to it. Okay, I'm going to stop now just for a moment and initiate the meeting for the NLP class. I'm going to go to my, I guess, Stack Overflow, or my email should. I'll be right with you then. Email. There it is. Okay, so if I do this, that should start the meetup. Join a meeting. Already another meeting. You want to leave and join this meeting? No. Now that meeting is there. It should be. People should be able to see that. Can somebody see if they can see that meeting now? The NLP meeting. Like this NLP meeting. We started. Okay. Can somebody check and see if that NLP meeting is now up? Hello, am I being heard?
Yeah.
Did I lose? Yeah, is it up?
Yeah.
Okay, great. Okay, let's go back to the, let's see. Am I still sharing this notebook or do I have to reshare it?
No, we are able to see it.
You're able to see, okay, so.
Right.
All right, so then after he does this callback handler class, he then defines this test callback class, which just allows us to run this thing and see that it works. So here he's just gonna modify this begin fit by adding a little counter. So it's going to inherit all the properties of the previous begin fit that we defined, but it's going to have this n iters counter that's going to be initialized to 0. And then every time you do a step, you increment this n iters counter by 1, and then you print it. So, and then finally, when n iters becomes 10, then you set this learn.stop flag, and it stops everything. So that's this test callback class. Now here is the refactored training loop with all the callbacks. This is the one that the one that I showed in the slide, but now it's all. I kind of expanded it out so you can see everything that's going on in it. So remember we have this one batch that processes one batch at a time. Then we have another function called all batches that takes as its input the data loader and a callback list. And every one of these things you've inserted a callback into so that it makes the thing more flexible. This one batch thing now can do something that's specified by this callback. And so what it does is it does all the things that the one batch is supposed to do, except with the additional flexibility that it has this callback state. You could check the state of the callback and have some logic depending on what the callback is. So in other words, here, for example, it says if the callback that you've given it is not the after underscore loss callback, then you can quit. But otherwise, in other words, that means you've already computed the loss function. But if you haven't already computed the loss function, then compute the loss function. That's what this is telling us. Then, if the callback is after backward, that means that it's time to update the parameters. So you do the step. Okay. If the callback is after the step, if it's the after step callback, then it's time to zero out the gradients. So you do that. So he's basically refactored this thing to now take into account the state of the callback list, that the callbacks that are given to it on the list, in the list that is that you're putting in. Okay. So, and then he's got this this function that processes all the batches, given the data loader, given a callback list, and it says, you know, for each batch in the data loader, process the batch, that is, do this one batch. And if the callback, if the do stop flag has been set, then you return. Let's see, what? Process the batch, then check whether to stop. I'm not sure what this is doing. So I understand that it's saying process all the batches using the one batch function, but then it says if the do stop flag has been set, then return. Oh, I see. That breaks out of the loop. Okay, so this is the loop over batches, and it says process the current batch, then check if the stop flag has been set, and if it has, then break out of this loop. That's what's happening here. Okay, and then here's the fit function, refactored this way. If the callback is not in the begin fit state, then break out of this loop. Otherwise, loop over the epochs, check whether to start. Well, if not callback.begin epoch, so if it's not in the begin epoch state, then continue. And then, let's see, epoch, all batches. So then you process all the batches, that's what this does. Remember, all batches loops through and processes each batch with one batch. Right, so process all the batches, check whether or not to process the validation set, so callback.begin validate. If the begin validate callback is there, then you process the validation set. And remember, when you do that, you don't need the gradients, so you do it with torch.nograd. You can run this all batches thing on the validation data. And then finally, check whether or not to break after the epoch after that epoch has been processed. Remember, this is the end of one epoch. If callback.doStop, if that stop flag is set, or not callback after epoch, let's see, callback.after epoch means you're done with an epoch. Let's see. So if that, there's some logic there. So you can see what this is. This is a Boolean statement, and it's going to have a value of true or false. If it's true, then break. That's what it's saying. And then once you're done with the fit, then you set the callback that says after fit. So it's basically telling you where you are in the loop. So that's integrating callbacks into the fit loop, into the training loop. That's what that's doing. All right, and then we run the train. Okay, let me run this. And then we can actually run the training loop with the test callback, and this is what we expect. It's gonna print the epoch number, and then it's going to stop when it gets to 10. So that's, whoops, something happens. The object has no, I must have not executed something above. Let's see, I better just make sure that I've done that. Maybe I haven't done that yet. Do that. Do that. Do that. And finally, now it should work. Yeah. There it is. So that's exactly what you told it to do. It says it's running through the epochs, and each time it prints the epoch number, and then when it gets to 10, it stops. Okay, and then he refactors the callback class, and it's basically adding a name property and an order and run attributes. I'm a little confused about what this order is, but he makes use of it. So this is for later use, because you can see this whenever you see this sharp pound export. That means that here's something we've built that we want to pass on for the rest of the course, that we're going to be using in the rest of the course. So it means that this is an important function or class. So he's basically refactoring it, adding a name property, an order and run attribute, and set and get methods. And then he got this cool little function. I don't know much about I've seen regular expressions, but I'm really not good at at parsing what these things are. I can do it, but it takes me a long time to figure it out. So, but what it's doing basically is this function is converting a camel class to a snake class. And what I mean by a camel class is when you have something that starts with a capital letter and every word is capital, every new word is capitalized. This is, for example, this object here the name is in camel class, whereas other objects such as this is snake class. Everything is in lowercase, and there are underscores separating all the words. That's snake class, okay? So he's built this little function that takes the name of the class, which is in camel case, and converts it to snake case, and in that way it generates a name for this callback that's in snake case. So we'll see how that works in a little while. So I'm not going to go through it more than that. Then he builds this another class called train eval callback, and it initializes the epoch and iteration counts. If we're in the training phase, it increments the epoch and iteration counters. And here, each iteration represents a fraction of an epoch, where n iters is the, I think n iters, where does that come from? N iters. I'm a little confused here. N iters is the total number of iterations. So if you set it to be 10, let's say, if you said you want the training loop to run for 10 iterations, then every time you run the training loop, you've got 1/10 of an epoch done. And when you run 10 of them, then you have one whole epoch done. So this is basically telling you where you are in fractions of an epoch. Okay. And then you're also iterating. So this is going to be a floating number that can go from 0 to 1. And then this is the number of iterations, which in our case, it runs from 1 to 10. So, oh, sorry, 0 to 10. So you can see here, n epochs is initialized as a floating point number. N epochs. Oh, not that one does n epochs. I think I've refactored this a little bit, and this may be. Oh, the one I started for. I've a message to check the meeting that I started for Avinash. Let me check it. I may have started the wrong meeting. So I looked in the email for the CS224N study group. I started that one, and it looks like 396-99436. Yes, that's the one. So, sorry. That's the one I started. Okay. Back to the notebook. Okay, so then he defines this train callback thing and this train eval callback class. And what it does is it switches back and forth between training and validation, and it maintains an iteration count and a fraction of the elapsed iterations in the epoch. And I refactored a little bit because I wanted this name to be more descriptive, frac epoch. And I think I forgot to n epochs instead of, that was what it's originally called, and I'm calling it frac epoch. So that's a little error that I just found and corrected. Frac epoch. So frac epoch is going to be a number between 0 and 1, and it tells you where you are in this epoch. Like if you know that you're going to do 10 training iterations and you've done 5 of them, then you're halfway through the epoch. That's what this is going to be. And there it is right there. Okay. Execute the training phase and self.run.n epochs equals self.n epochs. Self.n epochs. So in-train equals true for the training phase, and in-train equals false for the validation phase. And I got to figure out what this one is for, this n epochs. N epochs. So this should be, I'm setting n epochs in this begin epoch function as frac epoch. That's what it should be. Sorry about this refactoring in the middle of it. But that's what I defined. This frac epoch is going to tell you how far you are through this epoch, and that's what I should have. I had made a mistake by not putting